This video is part 2 of 2, so it's the conclusion of the refurbishment of my Heathkit IO-18. So to get more context out of this video, you should probably go back and look for and view part 1 of this, and I'll put the link in the description if you can't find it in the channel. So that'll just make sense. So at this point, I've spent some quality time online with Mauser to collect and have shipped me a whole bunch of parts, which I would need to, which you're going to see to swap out here. Those parts have all arrived. So we're going to start swapping parts, mostly, frankly, capacitors, as you would expect. We're going to start with the desoldering of the PC mounted, not chassis mounted, the PC mounted 3-section electrolytic can capacitor, which was causing me anxiety in part 1 in terms of how the heck am I going to remove this mess without completely destroying its PC board that it's on. So without further ado, here we go. And flipping the board over, or the scope over, here's the underside, and sort of in the middle of the picture you can see where the can is soldered straight to the PC board. There's actually 6 solder connections. 3 of them are the tabs that form the case and the ground connection, and these are twist tabs, if you know what I mean. And then the 3 in the middle, also arranged in an inner triangle, are the 3 capacitor positives, which are also nicely twisted tabs and soldered just for good measure. So as you'll see, you have to not only get the solder out and untwist the tabs and try and get enough solder out so the whole thing slides out. Spoiler alert, that's not exactly what happened. The only redeeming feature here is that this obviously is a single-sided board, and so there's no through-hole plating to trap even more solder and make life even more difficult. But nevertheless, we'll get our Hacko FR301 desoldering tool, indispensable, out and start at it. But first, let's clip some of the wiring. There's there's a jumper there which was in the way, and so we'll put that back once everything's done. But we have to get rid of that. So here comes the Hacko FR301 desoldering gun. Again, an indispensable tool. I thought this would be relatively easy because this tool really does make life easy to desolder things on PC boards, but in this case, because of the fact that the tabs are twisted, not exactly. Boy, am I having fun here. Time to add a little more heat. So now I'm starting to get desperate to try and get the solder flowing even more nicely. So the good news is enough solder is coming out, but not enough to fully liberate. In hindsight, maybe I should have tried to use some desoldering braid. I'm not having fun. Yeah, that's about as good as it's probably was going to get using the desoldering gun. Again, at this point, I know I'm getting frustrated with it, and I'm about to go medieval on the whole thing, and would rather do that off camera because it's truly ugly.
I had to take away the camera because it was getting in the way, and I kind of had to get medieval on the capacitor's various ground lugs and positive lugs here because they just wouldn't cooperate. Unfortunately, it's cost a couple of pads, but not traces, so that's not too bad. A couple of the traces are still good, but this pad lifted off, and then it looks like this pad lifted off. So the three middle ones are the three positives of the capacitors, and the three outer ones here are the ground connections. This ground connection is going nowhere. This is a single-sided board. But notice this one was connected to here, and this one was connected to here. So I have to make sure when I put the capacitor in that I run a jumper from here to here, because that was being assured by the case. And I've confirmed that these two are meant to be, are in fact ground. Certainly this one is, and this one winds up being ground as well. Plus there was a little wire here whose insulation went away. This was connected to the positive of triangle capacitor, so I'll have to put that, make a jumper to put that back. So not too bad. We'll have our little triangle of 22 mics at 450 mounted on the other side, and they should poke through these holes pretty nicely. Just for fun, let's see what shape this can is in. So we'll start with one of the caps here. 26. This should be 20. This cap here. 25, 26 as well, and then the final triangle one here. 25. So they all read about the same, and they're within range. So actually, so far so good. Since we have it, let's take a look at the ESR of this thing. I know it's not shorted because the scope did work, and it would not have worked if it had shorted. So let's go between ground and this guy. We have 1.5, almost 2. This guy's 1.5. This guy's also 1.5. This guy's a little higher. So this doesn't tell me anything about leakage, but it does give me an indication. For example, if I then look at what's going to replace this can, which is this little triangle arrangement of 22s at 450. Notice all the negatives are pointing outwards because that's this exact same arrangement that's here. So you have the negatives on the outside and the positives on the inside. I have to find a way of securing these three together, maybe a little tiny little dab of hot glue or something just to hold them together. But for fun, let's just look at the ESR of one of these. So about 1.5. Another one, 1.5. So yeah, that's what normal should be. So the can, obviously the can was working as a capacitor, but still, this thing is, I don't know, 60 or 70 years old, so not worth staying in here. So I was going to use a little dab of silicone sealant to hold these three together, but unfortunately all I have is this, and it's just not going to work. So instead I'm going to use a little bit of hot glue, and that should be just fine. So here are the three of them hot glued together. That actually came out nicely, with course with all the negatives pointing to the outside, because that's how this was. The other interesting thing is this should fit very cleanly in the existing holes, because the dimensions are very similar to the original cap. So if we look at the distance between the negatives, it's not that far off, and the distance between the positives is not that far off. So this should actually slot right in to the holes in the PCB. And just bend some leads out, make sure everything connects, and we should be good. Here's how the bottom of that 3-part capacitor came out. There's 2 black jumpers, and that serves to connect all the grounds together. In the past, that was being done by the case of the can. And then the red jumper is an existing connection which used to be there, which I had to put back. It feeds some B+ elsewhere into the circuits. But so even though the pads have lifted off, where you see the openings, it's alright. I was able to solder to the remains of them, and it all looks really decent enough. So here's the 3 capacitors that are substituting for our 3-part can, standing up and slightly glued together with a little dollop of hot glue. Here's the bezel, and what's nice is the bezel and the graticule and all that is held on by 4 convenient thumb screws here, which I removed all 3 of the others, and there's 4 little washers that come off.
More easily, one-handed, 1, 2, 3, and 4. There you go.
And bezel slips off nice and easily. Hey, this one is aluminum. The one on the IO-102 became plastic. Nice. This one's in good shape. Then we have a layer of plexiglass which protects the graticule, and that comes off. And this is in pretty good shape. We just have to clean it up a bit. Shouldn't need to polish it. And then the green plastic graticule, which is in surprisingly good shape. These often get torn or scratched, but this one is actually perfect. And if I do ever clean it, you want to make sure the ink is on this side, and you can tell from the 1, 2, 3 numbers, because if you would put it on backwards, it would be bad. So the ink is on the front side, which is probably why it's protected by a layer of plexiglass. So be very careful when you clean this. Don't use basically anything on it, because you don't want the ink to come off. And finally, here's the front of the CRT. These 4 grommets are part of the mounting system for the CRT. They're actually a little stiff, but not so much that they aren't doing whatever job they're supposed to be doing, so they're staying in place. So the rear board here is the horizontal and vertical deflection amplifier board, and there's the 40 microfarad electrolytic here, which we will replace. But while we're at it, we might as well replace these guys. There's 4 of these. These are 0.1s. There's one here, there's one here. They're identical. I have to look at their voltage rating, but that's unimportant because we'll replace it by something suitable. So we might as well replace those 4 while we're at it, because we have beautiful access to the rear of the board. So why not? Sometimes it's hard to figure out if you're looking at the front of the board here, and I want to desolder this this 0.1 cap. If I go to the back of the board, you know, where are the 2? Where's it soldered to? It's not obvious which holes it's in. So the way I'll do it is I basically shine the flashlight as straight on as I can. And that shows me that it's basically this one here and that one here, because you see the shadow of the cap is right there. So that's a little tip I use if I want to just quickly identify which solder pads belong to what component. Obviously, this really only works on a single or maybe a double-sided board. Here are the 4 on the left, 0.1s coming out of the vertical deflection amplifier board. These are 0.1s at 200 volts on the left, and since I had them out, they're replacement, also 0.1s, but these happen to be 400 volts, so these will go right in. Here's the back of the scope, the horizontal and vertical deflection plate amplifier board, and a fair amount went on here. Basically, this was completely recapped because it was easy to get to the rear of the board. There's one electrolytic here. This was it became a 40 at, or 39 at 450 volts. This is basically one of the long, skinny radial capacitors, which I turned into an axial capacitor, because it's getting hard to find axial capacitors. Notice it's on its side, and the negative lead, the one that's shown by the white stripe there, is bent back and over, and then down through some black shrink sleeving into the circuit board. The reason I chose to put it in this orientation is because the longer exposed lead is going to, what you can see on the right there is a ground plane, and so you want, if something's going to be exposed like that, you want it to be on the low impedance side of the circuitry. The positive goes straight into the PCB and to the presumably more sensitive parts of the circuitry. And moving away from that, there's our 1V2. Here's the main replacement for the 4-section electrolytic can cap. And I'll put the specs on the capacitors I used on here. It's on the little PC board, which can hold 4 such capacitors. And again, I chose to raise it a little bit off the chassis, because the solder connections on the board would be a little too close to the edge of that hole. So that's why I raised it about 5 millimeters off, and it looks pretty good. And again, on this side, here's the 3-section can replacement. This is not going into an adapter board because it's going straight into the PC board. And then everything else here was recapped, with the exception of another one of those 0.1 600 volters down there, which was just a pain to get to and is working fine. But I did replace one of the larger timing capacitors up here for the sweep. And that basically does it for the sweep section. Now here's another cap, which I had to sort of jury rig, so it could replace what was an axial cap. And so that's the left-hand side of the scope. This is the underside of the 4-section discrete capacitors in their PC board, and this is the hole that the can used to mount through. Because there are no tabs on this, I added my own terminal strip right next to it, and just under that big resistor you see there, and then wired things appropriately. I did move the 2 resistors. There's a power resistor and then a 2-watt resistor. I moved those, replaced those, and moved them over to the terminal strip just for space sake. So that's electrically exactly the same, but rearranged physically to accommodate the replacement capacitor board. The 1V2 rectifier tube, pull it out gently, and so here it is, again, the world's simplest tube. There we are, 1V2. I'm going to put that aside, and I want to focus a little bit on this socket and the way it's mounted, but we want to go to the back side of the socket. Here's the back side of the 1V2 socket, and you'll notice there's only 3 connections. Here, the 2 combination filament and cathode connections, and then 1 plate or anode connection. And so this is a rectifier. And it seems like they've changed the socket here to something a little bit better. I've seen a video of this scope where This screw is, the mounting screw is substantially closer to this connection here. And this connection here, according to the schematic, has at least negative 1400 volts on it when it's in operation. And of course this screw is grounded right now because on the back side it's touching the chassis. So there is, you know, what, 2 or 3 millimeters separation here between the 1400 volts and ground. I don't think that's enough, so we're going to address that. And here's how we made the 1V2 socket just a little tiny bit safer, all in the interest of making the overall operation of this scope as safe as possible. Anyway, the 1V2 is now recessed. Notice the 2 nylon screws and nuts holding the socket down. We're going to look at the other side. Here's the 1V2 socket. We now recessed it a little bit using 5mm nylon spacers and screws and nuts. So it's recessed a little bit further back, and that eliminates the possibility of the high voltage leads, whether it's the anode or the filament, touching the chassis or the screw there, because of course it's all nylon. A little bit of heat shrink added just to make it ever so slightly safer in case you should brush up against it. You shouldn't. You might ask why I have an extra bit of red heat shrink here with no wire coming out of it, and that's because the anode of the 1V2 internally connects pin 1 and pin 9 to itself. So either you could connect the black wire to either pin 1 or pin 9. Works exactly the same, but just again in the interest of safety, we want to insulate what's pin 1, even though it's not going anywhere. It would have something like negative 1400 volts on it. The other pins I checked have no voltage on them at all. They're not internally connected to anything on the 1V2. So again, just trying to make everything just a little tiny bit safer in operation. If we follow the 1V2's anode, another this negative high voltage connection, that goes directly to the brand new 1600 volt 0.1 filter cap network with a brand new 470K resistor in there as well. So here's the AC input section that I completely rewired using the same terminal strip but moving things around. First thing you notice are the 2 big rectangular things. Those are the X1, Y2 safety capacitors, which go from line to ground and neutral to ground, and that's for EMI suppression. Right next to that is our fan favorite CL90 input current limiter, PTC. And so the way that's wired is the hot line from the AC cord goes first into the back panel fuse, then it goes into the front panel on-off switch, then it comes into the CL90, goes out to the transformer, and then back from the transformer to the neutral side. Here's the beauty shot, if you want to call it that, of all the victims of this refurb. Virtually, there's only 2 resistors that I replaced because they were in the way, and yeah, the big one was a little bit out of tolerance, but not too bad. It could have lived. Surprisingly few electrolytics because most of them are in the cans. I always find these electrolytics fun. These Heathkit used a lot of these in the 1970s. This is like a 40 at something, but what's amusing is the paper tube rotates freely around the guts of the capacitor. Loose electrolytic here. And yeah, here's a 3-section can that got replaced. And yeah, here's was the main 4-section can. I had to get a little bit medieval to get it out because it kit builder had aggressively soldered the tabs, and well, it's how it wound up. Testing these show that, you know, apart from minor leakage, they worked fine, but they did have enough. One of the sections on one of these had a little bit of leakage, so I decided it was worth replacing with modern caps. So the rest of these are just paper caps and replaced with modern films. So anyway, this is everything that came out of the scope. One thing I noticed about the IO-18 is of the 5 Heathkit oscilloscopes that I own, and just those are the IO-17, 18, 21, 102, and the HO-10, which is sort of an oscilloscope. Anyway, of those 5 CRT devices that I own, the IO-18 is the only one whose CRT did not come with any kind of metal shielding around the CRT, the mu metal or magnetic or otherwise shielding. So I thought that was interesting, and it did not come that way from the factory. To its credit, they did decide to put the power transformer on the underside of the chassis to kind of shield it from the CRT. But some of the later Heathkit scopes went even further. For example, the IO-17 puts the power transformer in its own little sort of recess under there with walls on 2 sides. And my IO-102 actually has the power transformer totally enclosed in its own little 6-sided box inside the chassis, and of course has a shield. So I thought that was interesting. It was how Heathkit dealt with it progressively over the years. But yeah, this one has no particular shielding around the CRT. Something I've always wondered about all of my Heathkit scopes, whether they be solid state or tube, is the voltage rating on the potentiometers that Heathkit used. And I have to believe all potentiometers have some sort of maximum voltage rating, even if we don't think about it all that much. And the reason I think about it here, and the way Heathkit's always done things, is because this is the intensity control. This is the focus control for the CRT. And for good measure, there's also an astigmatism or pot shape control. But I'll just focus on these two because they're handy to look at. And these are in the high voltage divider chain that feeds mostly the cathode of the CRT to generate appropriate voltages to modulate the intensity and run the focus grid and so forth. The point is, these pins here, the 3 pins of the volume of the intensity and focus potentiometers, these pins here have on the order of, over negative 1,000 volts, well over negative 1,000 volts with respect to the chassis. And they're very close to the chassis, and they're very close to the actual metal part of the potentiometer. I won't even talk about the fact that this is the AC line cord coming in for the on-off switch, but it's noodling around there as well. But we'll just not worry about that. And I'm also not too worried about the actual carbon trace internals of the potentiometer being able to handle that voltage, because in fact the trace does not. Between going across the trace, now there's voltage drop of the potentiometer from one end to the other on the, I measured it, on the intensity is on the order of about 75 volts. And on the focus control, the voltage drop between the ends of the potentiometer is on the order of about 350 volts. So, yeah, but at least it's not 1,000 volts. But I always wondered, should these potentiometers be mounted directly on the metal chassis? Yes, it's grounded. Never mind that, these exposed terminals pose a shock hazard. So all of this to say that, well, be careful as you work on these old scopes, because they're all pretty similar in that respect. So here's the Heathkit IO-18 all finished and ready to go. Completely recapped and cleaned up a bit, and as you'll see, it's working great. As you saw in the power supply section, one thing I added was the CL90 inrush current limiter on the AC line, and it's amusing to see what effect that has when you turn the scope on. By the way, pardon the glare on the front panel, on the front face of the CRT. Here's our pilot light. It is an incandescent light. It's not a neon light. It's incandescent. This is old-timey, of course, and of course it's not an LED, but it is incandescent. And so when I turn on the scope, you're going to see how this gradually brightens because of the inrush current limiter, and I thought that's kind of nice to see. So here goes. You'll hear the click. See how that incandescent came up nice and slow? I thought that was kind of nice. Anyway, we'll let the scope warm up. And, oh, there's a dot. The tubes are warming up. And here it comes. And right now I'd simply have a little over 120 hertz sine wave that's on one axis and beating against a 60 hertz line frequency just to display something. So, in a nutshell, that's the IO-18 ready to go, suitable for continuous operation, and made to operate as safely as possible.